So this is near the near where we ended last time, but this is the reflectivity of some incident wave off at some interface with vacuum on one side, some material on the other. So written for an X-ray or EUV radiation. Again, angle of incidence we found equals angle of reflection, and we found that the refracted angle gets a little bit larger because there's this negative sign, and Snell's law gave us what the relationship, what this angle was for this incidence angle. And we had to do this for two polarizations, one where the incident electric field lies in the plane of incidence, and that's called parallel polarization. And the other case, the orthogonal case, is when the electric field is out of the board, okay? And that's called perpendicular polarization. You do them both. At normal incidence, of course, they're both going to be the same, but I wanted to start with this one today. So this is telling you the reflectivity for parallel polarization, which is the electric field, the reflected electric field, the double prime, that's this one, normalized to the incident electric field, it's this guy, and it's squared, okay? And this is what we found. If you just go through, and again, this would be the same material you would do in some classes on electromagnetics. And we're going to use this in a moment for what's called Brewster's angles. So I don't know how many of you have ever heard of Brewster's angles, but Brewster's angle occurs when the incident electric field is in the plane. So we'll come to it in a moment, and this formula is going to be repeated. This, by the way, is arbitrary for any angle of phi, okay? And for any lambda, that's all buried in the refractive index, okay, or photon energy. Okay? So that's where we were, where we ended, and we put in numbers for our refractive index, and basically it's simplified down to this, and we gave a single example to show that the reflectivity, for, which would work for either polarization, but we looked at perpendicular polarization, is this, get the same answer. And we put in numbers, look up numbers from the website that we use so frequently. And these were the values for F1 and F2. These were the values for delta and beta. And if you calculate it, it's less than 1 part in 10 to the 4. But if you remember, these deltas and betas involve a lambda squared. And so as you go from 4 nanometers down to 1 nanometer or 1 angstrom, these numbers are really going to drop quickly. Okay, so there'll be a homework problem just plugging in some numbers for hard X-rays. Okay, here's Brewster's angle. So what's so interesting about Brewster's angle? For Brewster's angle, it's the question is, or the observation is, that with the parallel polarization, there's some angle, Brewster's angle, for which there's no reflection. The amplitude of the reflected wave is identically 0. And so, for instance, this plays an important role in laser cavities. Solid state lasers always have the end mirrors, I'm sorry, not the, for instance, if they have a solid state rod like ruby or neodymium or something like that, or they won't cut the ends perpendicular to the axis of the rod, but they'll put them at an angle so that there's no reflection, there's no reflective loss. And so, so this is a phenomenon that happens at all wavelengths, and we're looking at it for X-rays. So here's the formula that we were looking at a moment ago. And if we, to find Brewster's angle, we ask, when is this reflectivity going to 0? So we set the numerator up here, set that equal to 0. So this part is going to equal this part. So, okay. And when we do that, there's a subscript appears B for Brewster's, okay. And you can square both sides and you can solve for this. And what you'll find is that the Brewster's angle is the refractive index divided, as you see here, by square root n squared plus 1. So For, let's say, for a visible light laser, n would be 1.5, and this would be 1.5 squared, so 2 point something, 3 point something. When you take it, you'd find out the angle is something like 60 degrees, as I recall. And so you'll see that on laser rods. But for us, if you put in our refractive index with delta and beta, what you'll find is that this angle with no reflection occurs at roughly 45 degrees because delta is extremely small. Okay, so that's mathematically why mathematically it says, okay, that's the angle. It's going to be 45-degree incident angle. There's going to be no reflection within this small displacement delta, angular displacement. So what's actually happening here? If the electric field is, if the wave, the incident wave is coming in here, so all across this interface, there's radiation coming in at this angle, okay, roughly 45 degrees. The electric field is always at right angles, so right at the interface, the electric field is oscillating this way. And if you remember our dipole formula for what happens with electrons that are now oscillating in this electric field, they're oscillating up and down. This is the axis of acceleration, the electric field direction. And the radiation is a donut pattern around that. So for every electron along this interface, there's a donut pattern. There's radiation going everywhere, but there's nothing coming back this way, okay? And you can just propagate that argument around, but you'll just see that at the interface, which is where you're generating your reflected wave, there just is no reflection. So that's the concept of the Brewster's angle, and it does happen at X-rays wavelengths. We had a beamline at the ALS, and we not so wisely overlooked this effect. And we tried to have an EUV reflection at 45 degrees, and we weren't getting anything until somebody realized we were in this so-called parallel polarization. Okay, so that's all I was going to say about that. Does someone want to comment? Yeah, by the way, so for instance, someone who's interested in magnetic fields or something, and you want to see a rotation, you want to see how some electromagnetic wave that's probing cobalt or iron or something else, how does it rotate? You need a polarimeter, something that can measure polarization and rotation. And one of the ways to do that is use Brewster's angle. So have two mirrors and maybe have one of them rotating in such a way that it always nulls out the field, okay? And you just track it, okay? After going through how much of the magnetic material, there's a Faraday rotation of the electric field of the polarization, and you can use this effect to track it. So it's a method used for measuring Faraday rotation and therefore magnetic field strength in magnetic materials. I'm not going to spend time on this, but there is this question of how do we determine F1 and F2, from which we get delta and beta, these atomic scattering factors. And there's a section in the book, you can read it if you want, but I think it's enough to say here that you measure the absorptive part, F2, and you measure over as wide a spectrum as you can. That's going to control your accuracy. And then you use these relationships that, for instance, F1, the real part, depends on F2, what you measured in the lab, okay, by this integral formula. These are called Kramers-Kronig relations. If you know either the real or the imaginary part over a full range, full spectral range, enough to get some accuracy here, you can get the other. And you just do this point by point. And there's some references here, but that's how it's done. In principle, you could measure both F1 and F2, but in fact, measuring the real part is a little difficult. You need an interferometer or some scheme like I showed you last week, where you have mirrors and beam splitters, and flat beam splitters are really difficult to make in the X-ray region. So there are a few cases. Regina Soufflé did that with Eric Gullickson as part of her PhD thesis in electrical engineering, but in general, it's not so easy. We talked in the first lecture about how now that we know we can have reflections off surfaces, even off bare surfaces if they're polished well, that we can take two curved surfaces and form an image. And depending on the geometry, how close this is to the focal length, we can have a very large magnification system, which is often the case. Okay, and the best image formation with these crossed mirrors is if they're both ellipsoids of revolution. Okay, and so I'll have some examples later in the lecture. Okay, so this is just pointing out. Okay, where are these glancing incidence reflective optics used? Well, for instance, at all the synchrotrons, most beamlines, but not all, but most beamlines have one or more mirrors in it. So this is a diagram of one where there are two spherical mirrors. They should be elliptical, but the difference between the ellipse and the sphere is not all that much. If it really matters, then you're going to have to get the ellipsoid. But for instance, if you just want to do micron imaging, the sphere is a close enough approximation to the ellipse. If you want to get down to nanometers, below 10 nanometers, I'm afraid you're going to have to go to ellipsoids, okay? So this is showing one example, and I just have a few others that I'm going to click through. This is a real beamline at the ALS. This is 12 point something, 12.0 something, it should say, but it's an undulated beamline at the ALS. And the first thing it has is a retractable flat mirror. It's just a mirror for sharing the beam. Depending on whether the mirror is in or not, it's deflecting the radiation to a certain beamline. If that mirror is dropped out, then the light goes straight through to a different beamline. And sometimes there'll be another mirror coming from the other side for a third direction. So this is a very common use of glancing incidence mirrors, along with other imaging mirrors. If someone wants to say something, just speak up. Here's one from APS, so hard X-rays. And here they have a silicon mirror. It says platinum-coated silicon mirror, and when it's inserted, it deflects the beam into their beamline, okay? Double crystal monochromator, etc. So we'll hear more about these things later. But those are examples. And I don't remember putting the angle in here, but the angle here would be pretty small. And unfortunately, I didn't put it. Okay, maybe that will be one of the homework problems. It's just a simple, what's the critical angle at some hard X-rays for some material? So Friday, I'll give you some assignment of problems. They'll be relatively simple, but you'll get numbers out of it. And I'll try to have you use the website we've spoken about so often a couple of times. So it asks you to show some curve of something or other rather than fight it yourself. The idea will be to go to the website. Okay, so this is examples of coated mirrors, sometimes coated, sometimes plain, sometimes coated. This is one at Spring 8, which is the largest synchrotron in the world, and it's in Japan, not too far south of Osaka. And they are the leaders in the world in making ellipsoidal mirrors with coatings, without coatings, with multi-layer coatings on it. And they have been able to use the two mirror pair. It shows here for a 25 nanometer and 30 nanometer spot size. So there's the undulator radiation, the double crystal monochromator, an aperture to use a smaller part of the beam. This has to do with off-axis aberrations in your optics. So just a controlled spot. And then the optics focus the radiation down. And among other things, they use a knife edge to measure how wide is the spot size in orthogonal direction. So these are both orthogonal to the beam. This is one of the references. There are more references in chapter 10 for this group. And this is the group of Yamauchi-san, Professor Kazuto Yamauchi at Osaka University. But they're very close to Spring 8, so they go there a lot and they make these measurements. And besides this focal spot to 25 nanometers approximately, they've also done to 7 nanometers in both directions. So they hold the world record on this. And I would say that for synchrotrons around the world, which there are more than 30, and free electron lasers around the world, there are now a half a dozen, they all buy optics, which are an outgrowth of Yamauchi's group. So he started a mirror, he started a company that makes these sophisticated mirrors, and it's called JTEC. You could just do a search for JTEC Japan, and they make the best mirrors in the world. And for anyone who wants to make a microprobe down to under a micron or something like that, basically all the synchrotrons and FELs in the world go and buy them from JTEC. And they have lots of applications. I didn't show the applications here. This is showing a nested mirrors, a whole bunch of nested mirrors. And these are called Walter optics. They use pairs of conical sections. Different kinds get different names, Walter 1, Walter 2, etc. But this is showing a set where light from the distant cosmos comes in and is brought to an image. It says focus, but it images these stars, for instance, or galaxies onto an electronic detector. And this is this is an image of the so-called Whirlpool galaxy, M51. And this image is not all X-rays. It's a it's a composite of visible, ultraviolet, and X-ray images. And it shows how these stars seem to be in a whirlpool pattern. Okay, and I have to turn on. I usually leave my phone on so that if something goes wrong and you need to contact me, we can reach each other. But I'll turn it off now. Yeah. So so there's a gazillion of these images. If you want to read a little bit more, you can just go to Google and look up M51, or just look up Whirlpool Galaxy and it'll get you this. And the galaxy, by the way, they say has about 100 billion stars, so 10 to the 11 stars. They wonder sometimes how many stars could there possibly be in the galaxy? Well, a typical galaxy would have something like 10 to the 11th stars, or something a little bit more than that maybe. And there's something like 10 to the 11th or 10 to the 12th galaxies. So when you multiply those two numbers, you get estimates of around 10 to the 23 stars. So this was a good project for people in the last two classes where they were from the physics department and they were interested in astrophysics and they did things. But anyway, you can see their use here, where these optics are either uncoded or more likely they have something like iridium or something which picks out a certain part of the spectrum that they want to see. In fact, yeah, okay, so here's some example of mirrors that are used where their cutoff, for instance, iridium is cutting off around 10 kilovolts. So it's blocking radiation above 10 kilovolts, but accepting radiation down below 10 kilovolts. And in fact, I'll show you how they make a filter that's not super accurate filter, but sort of gets a window here of radiation. And then they'll have another one here. What they do is they combine a mirror and a filter. I'll show you in a moment. But anyway, this is showing you 3 mirrors that give you nice sharp cutoffs here around 800 eV, here with gold at 2 degrees, again around 2000, etc. Okay. So here's what they call a notch filter. The mirror reflectivity, no units on this. Mirror reflectivity is shown in red. It's like this. They call it in certain communities, they would call that low pass. It passes photon energies below some energy. And they combine that with an absorption filter, which has an absorption edge, and it allows things to go at higher energies. They can just go through the filter like butter, maybe 90% or more getting through. So that's a high pass. And there's this little notch here right around the absorption edge. And if you combine an absorption filter like this, let's say an aluminum filter, the high harmonic people would know about using, let's say, aluminum filters or something like that. But anyway, if you combine a mirror and a filter, you can get a notch here where it's a broad band, so you can get a lot of photons and you can measure something or form an image, but the spectral width would be E over delta E of around 4 or 3 or something like that. So this is a very common technique. We use it all the time in the lab for plasma physics for sure, for astrophysics, and we also use them on beamlines and high harmonics.
Professor?
Yeah, please.
Can I ask a question on slide 37?
Yeah.
So I understand that like for the blue curve, the filter transmission, that you say that like higher energy can transmit through.
Yeah.
But I'm confused about the low pass part.
This part.
So the red curve.
Oh, the red curve itself. So the red is for the mirror, right?
So what does it mean? Because it says like at lower photon energy, it has 1, like it's 100% reflectivity for the mirror.
Yes.
So wouldn't that mean that like for lower photon energy, it actually
so the mirror is letting through all of the lower photon energy. So let's say this was a kilovolt. This was 1,000 eV. This says that the mirror is reflecting very nicely up to something like 700 or 800 eV, and then it starts dropping. So it's low pass. It's passing all the lower photon energies. And in fact, if we go back another one, that's what's happening here. If we look at, just say this nickel mirror, it has a decent reflectivity for lower photon energies, but when you get up here around a kilovolt, it just doesn't reflect anymore. And it has to do with the critical angle. So all these mirrors are called low pass. They allow things to come through on the lower end, but they block higher photon energies. So one of these curves you could imagine is this red curve. It's just artistically drawn.
Okay,
now,
so like, oh
yeah. So clarify the question again. How did we do?
So is it like when you say like the mirror allows a lower photon energy to pass through, are you saying that it's like allowing it to reflect basically?
Yes, it's absolutely perfect. Yes. It's deflecting, the angle is changing, but basically it's having a near 100% reflectivity. It could be 80%, but it doesn't matter. It's allowing a lot of photons to reflect off very nicely in a certain region. Let's say if this was 1 kilovolt, below a kilovolt. So that blocks high energy photons. So you're trying to do an image. Let's say you want to see, like we showed images of the sun that were formed in 8 and 9 times ionized iron, IRON. Okay, and we wanted to form an image of the sun that's looking at the iron content. So you want X-rays just from that particular energy. And I believe it was something like 200 EV, is that right? I forget. But anyway, so you'd like to have something that would give you just block some of the high stuff and block some of the low stuff. Just focus on whatever photon energy you're interested in with enough width that you get a lot of photons and you can still form an image.
Okay. Yeah, got it. I think at first I was confused because like, I guess like when you use low pass and high pass, it all depends on what optics you are talking about. Because like at first I was confused because like for transmission, like high pass means you're allowing things to pass.
That's right.
Like pass through. But like if it's a mirror, like passing means reflecting.
I got you. Okay, now I see the confusion. But anyway, this is the phrases that they use. These are kind of like um, electrical engineering terms for a filter in a circuit. They call them low pass, meaning low frequencies are allowed to go. High pass, high frequencies are allowed to pass. But
Okay,
you're right,
got
it could be confusing if, okay?
Thank you.
Good, thanks. I may have shown you this before, but I'm going to put in some stuff about multi-layers now, which is from chapter 10, and a little bit of imaging. I think we did so much math the last few times, I wanted to break that up, and this sort of fits well with reflectivity. So I'm going to show some multi-layer stuff and some imaging stuff, and I think we'll be done with that today. So this is an early multi-layer mirror. In fact, I forget what it was. I think it was maybe tungsten carbon. Could have been polysilicon, but it was student Tai Nguyen. He was both in material science and he was in AST. And this is a kind of curve at lower, in the visible, we have great reflectivity mirrors, and high energy X-rays around 10 keV, 20 keV. We have natural crystals, which can give you basically so close to 100% reflectivity. But there's a middle region here where there isn't much choice for normal incidence mirrors. And this is just showing a few of them that came along. Before multi-layer mirrors came along, there was nothing in the middle here. Okay, so between, let's say 20 or 30 EV up till many keV, 6 or 8 keV, there was a void. So multi-layers fill that. This is an example I showed you before. This is polysilicon. It's got 40 layer pairs, and the D-spacing, which is one period, it's one black and one white. This is a TEM side-on view of a thinned multi-layer mirror, and this is showing how incredibly beautiful it is with nice flat curves. So the moly would be the darker, it's scattering more electrons out of the TEM, and the whiter would be the silicon, not scattering so much out. There are some comments on how do you make a high reflectivity mirror? Okay. So you need contrast, refractive index contrast at the interfaces. So the deltas and the betas have to be different for the two materials in order to get a reflection. If they were both the same, the electric field wouldn't sense a difference. And so there would be no reflection. So you need a contrast in the deltas and the betas. And basically you want as little absorption as possible in the low Z material. And the high Z material, it's helpful if you could make it a little thinner so there's not as much absorption. You still have the same number of interfaces for the reflections, but if you can make the high Z layer thinner, well, that will help with your what kind of reflectivity you can get. Of course, if you're getting down to nanometer dimensions, it may not be so easy to make the high Z layer thinner. You may not be able to have much control over that. Certainly you need interfaces which are chemically stable with time. You do your coatings and on some substrate, on either flat or curved substrate, you put it in the closet till you're ready to use it, and you hope that when you take it out a few months later, it's still doing well. So that goes into many of the choices for the mirrors, especially the ones that are going into outer space. When you put them up there, they're going to be up there for years, and you hope that they're both chemically stable and interdiffusion stable. You don't want the moly going into the silicon and the silicon going into the moly, because then the interface isn't so sharp. Same like for tungsten and carbon. Okay, so sometimes you'll see we'll put a diffusion layer at the interfaces. You don't want the interface to be rough. You want it to look as flat as possible. And so you don't want little crystal formations in any of the layers, because they just bring a non-uniformity to the refractive index that the incident wave sees, and a little crystallite formation is just going to scatter radiation in other directions, not what you want. So you want smooth surfaces and no crystal formation. Okay. And they have to be thermally stable. For instance, at the undulated beam lines, they're going to take a lot of heat load. Okay. So this is an example. It's from Sasha Byte, who was at Lawrence Livermore at the time, but now she's in Germany, in Hamburg. And this is a diagram that we made together of how a polysilicon multilayer might look with these little yellow interface barriers. So that's because when you're putting down your coating, so you start with a substrate and you put the light, let's say is silicon, you put that coating down, and then you're going to put moly on top of it, and the moly atoms may start to go in a little bit, diffuse into the silicon. And so then the density, the gradient at the interface, the sharpness of the density at the interface won't be as good. So this was so Sasha's idea to put in B4C, thin layers. You look at this. This is 2.5 angstroms that she's putting in here, and it's asymmetric. It's not the same on both sides. And this gamma equals 1/3. This was the ratio of the thin layer, the high Z layer to the low Z layer. I said you'd like to make the high Z a little thinner, and here it is thinner. As a question, I'm going to show you how to do a quick estimate. How many layer pairs do you think you need to get a decent reflection here? Oh yeah, so this is measured. This was measured by Sasha, and she was the first one to get a reflectivity of up to 70%, 70.5 or something like that. And that she held that record for more than a decade. Now there's a few other of the commercial people making coatings who have gotten into the same place, perhaps a little bit more, but for instance, not more than 71%, as I recall.
Professor?
Yeah.
Just curious that I used to make deposit the layers.
Can you repeat it? Because there was a loss of a few words as you were talking.
Oh, I was just wondering what method did they use to deposit the layers one by one?
Okay, I'm going to show you a slide. I don't know if it's the next, I think it's not the next slide, but it's coming real soon.
Okay, thank you.
Yeah.
I also have a question.
Yeah.
This extra layer that limits interdiffusion, how does that affect the reflectivity? Like, I understand how interdiffusion would affect it, but how does adding this layer change things?
It's relatively thin compared to the wavelength. The wavelength's 13 nanometers, and this is, small. And so I think, and it's all low Z materials, boron and carbon, so it's not absorbing a lot. It's not absorbing a lot. It is changing the definition of the interface a bit. It is giving some thickness to the interface, but bottom line is, if they analyze it, they make it, and it works pretty well. So here's the reflection coefficient. Oh yeah, so this I just made up before, while I was waiting for you guys to come for class. What an estimate of how many layer pairs would you need to get a decent reflectivity? I should have made this, what do you need to get a reflectivity of 50%? But it required one more step in this little derivation. So I just said, I did it differently. So I went to the website we've talked about before, and I looked up the refractive index for molybdenum. I see I lost my capital M, and silicon. So this is the delta. I looked up the deltas and the betas for moly and silicon at this photon energy and wavelength, which is what's used for the lithography. And we saw before that the intensity, the reflection for intensity, would be delta squared plus beta squared over 4. And it turns out here that the silicon, the delta is so small, it doesn't matter. It's like vacuum. So we can make this estimate just using the delta from the moly. And the betas are both, they're rather similar for one thing. So there's not going to be much contrast, but they're both small compared to this delta. So it winds up that in this case, the delta squared plus beta squared over 4 is roughly equal to delta over 2 squared. right, the beta squared doesn't matter, so it's delta squared over 4, and I just wrote that as delta over 2 squared, and I did that for a reason. This is an intensity reflection, but you know that the electric field, the intensity is proportional to the E field squared, or putting it the other way, the electric field is proportional to the square root of intensity. So if the intensity reflection were down by a factor of 100, the electric field would only be down by 10. Okay, so what I then said was, okay, if the electric field, if the reflectivity of the electric field from a single layer is roughly delta over 2, then how many interfaces do I need in order to get a reflectivity of order 1? This is where I might have said a half. And that would mean just flipping this. So it would be like 2 over delta. So this is saying that you would need about 26 interfaces. So again, the intensity reflectivity was one thing, but the electric field, it doesn't take as many. Okay, and that's because at each of the, I should have a diagram here, but as the wave comes into this multi-layer and it's reflecting off each layer, again, it's a little bit like a crystal, but amorphous. But anyway, the reflections at the Bragg angle, all the electric fields are adding up in phase. And that's why you get away with this square root. So anyway, to get a reflectivity of order 1, it would be the inverse of this. And you'd need about 26 layers, each giving this much of a reflection in order to get something approaching 1. And that's 26 interfaces, but that's a number of layer pairs, moly and silicon, moly and silicon. You get 2 reflections for every period, so it's only 13 layer pairs. So I went to the website and I looked up, okay, for moly silicon at this photon energy, if I only have 13 multi-layer layer pairs, it predicts a 42% reflectivity. So not 100%, but 42%. So I would say that was good. I was happy with that because we didn't include absorptive losses within each of the layers. But it gives you an idea that in the EUV, where these values of delta can be quite high, you can manage to make good coatings. This is just a simple diagram, and it's showing, you know, the alternating materials. What is a D spacing is 1 layer pair. Okay, here's the angle of incidence at some wavelength, and this is just a made-up diagram of electron density I'm showing here. And so for moly and silicon, the electron density is going to be lower in the silicon than it is in the moly. But what I really wanted to get across was the idea of these sharp interfaces. Okay, and I'm going to show you in the, I have to show you 2 things. One is this, there is actually, when this incident light comes into the multi-layer, there's a refractive turning, and it has to do with delta. And this is an average delta over 1 full period. And so this used to be a homework problem we would give all the time. So the Bragg's condition, Bragg's law, is modified by the refraction of this incident radiation. In fact, by the way, although this is clearly a small quantity because delta is small, this was really confusing for the first people who were working on reflection from coatings. They were getting certain answers, but they always felt that their answers were off by a little bit. And it turned out that they, in the early days, were not including this little bit of refractive turning. Okay. And here's, suppose you don't have sharp density variations as shown in the light gray, grayish blue. Suppose it's more mushy at the interfaces. Here I'm just showing if, okay, let's do a Fourier analysis of that. So the red is showing the fundamental, okay? It's always peaking at the peaks, and it's always a minimum at the minimum. And if these things are symmetric, there'll be no odd terms, okay? Because this and this are equal. but there'll be no even terms, I should say. So there'll be no n equals 2. So the red will be like n equals 1, the fundamental. This blue is n equals 3. There's no even numbers because of this, because of what you see as the symmetry. So if this was not so sharp, you'd have some third harmonic representation. So if you did a Fourier transform of the density function, you get something like that. And then, okay. And this is showing down here that although in red might be picking out the reflection off the primary period here, the blue is coming in at roughly 3 times the angle, and it's seeing 1/3, it's seeing a density modulation of 1/3 the period, and it's reflecting at a different angle, okay? So in fact, if you make a multilayer and you're wondering how sharp are my interfaces, one of the things you do is you'll go to the lab and get a copper K alpha source at, what is it, 8 keV, 8.9 keV, someone remind me? And you just scan the angle and see the different harmonics that will appear. So, and it'll tell you what is the sharpness of your multilayer. So here's some measurements that were made by Yan Wu, who was a student in the physics department, and James Underwood. And they're showing as a function of angle, as they scan, always with fixed wavelength, 1.54 angstroms, as they scan, they see the high reflectivity at very low angles that any mirror would have, any interface would have. This near 100% for very small angles. So this would be the critical angle right here someplace. And then you go out and the coating on top of it picks out a peak. This is the Bragg peak. And this is the second Bragg peak and the third and the fourth. So the fact that the second and fourth appear says that these two layers, the two layers, the tungsten and carbon in this case, are not equal thickness. So that's why you're getting some even harmonics appear. And this is telling you, this gives you information then on how sharp your interfaces are. Yeah, how are we on time? Oh, we're doing good. I don't remember if I showed you this before. This is for a crystal. We'll talk about it for a multilayer in a moment, but this is showing a crystal, sodium chloride crystal, I believe. And so here's a plane of, maybe it's the sodium atoms, and then there's a plane of the chlorine atoms, and then a plane of sodium again and again and again. And they're in very beautiful flat planes. And this is the despacing here between the different layer pairs. And so you come in at some angle measured from the horizontal. That's the way we do Bragg scattering geometry. And the radiation comes in, and there's a reflection basically. First of all, we know that there's scattering off every atom. And the scattering goes in all different directions. But at certain angles, the reflections add up in phase, and that magic angle is the Bragg angle, okay? So so some people, in fact, Bragg, the younger Bragg, he was like 21 or 22 at the time. He was a college student. His father was a famous X-ray guy, and they were on vacation. And the younger Bragg said, the older Bragg had just learned about these reflections had been seen in Germany. They're British, English. And they went on vacation, and the father was talking about the fact that at certain angles there were these reflections. And the younger Bragg said, it looks like it could be that they're just reflecting off interfaces. And it's a phrase that was used, and that's how he, the younger, developed what is Bragg's law. And it's Bragg's law, it's a singular Bragg. It's not the two of them together. They had a lot of papers together, but this Bragg's law is just the younger. And so anyway, there are all these reflections. And when you get a really strong reflection like this at the Bragg angle, the incoming wave and the outgoing wave are pretty similar in magnitude, okay? And so they interfere. and there's a standing wave in this direction into the crystal. And that's what's shown in the picture on the right. This is supposed to be, the purple is representing energy density or something like that. And it's just giving you a close-up view. So here's electric field squared, what it is. So the standing wave is forming an E squared pattern where there's very little electric field at the actual planes where the atoms are, and the electric field is maximizing between them. So you know these little pictures of black dots and white dots, that's not accurate. That's what it is that's where the core electrons are. But the valence electrons are what's setting the distance between the different planes. So the outer electrons, the valence electrons, are reaching in, and that's what's separating the two different planes of material. And the valence electrons are relatively free electrons. The core electrons, which would have more to do with X-ray absorption, are confined pretty close to the planes in each case, so that there's very little absorption because the interference pattern is giving very little electric field right at the planes. So that's a concept to swallow. Could somebody break the ice and talk about that? For instance, we talk about the Bohr radius for a hydrogen atom, principal quantum number n equals 1. The Bohr radius is 0.529 angstroms, roughly half an angstrom. What happens for, let's say, sodium or chlorine or something like that, where you have a lot more electrons? What is the radius, not exactly, but what is the radius for the n equals 1 and let's say n equals 2 electrons in each of those atoms? It's actually a lot less than the Bohr radius. When you go to a higher charged nucleus, it takes the electrons in the lower orbitals and pulls them in much more tightly close to the nucleus, okay? And it's only the the valence electrons which are out around a Bohr's radius. So that's why here, in all of these cases, the core electrons, principal quantum numbers n equals 1 and 2, are very tight to the nucleus, very close to the nucleus. And it's only maybe the outer shell of electrons which is yielding this separation of the planes. So this interesting effect of the incoming and outcoming forming a standing wave and interference pattern, okay, it only happens at the at the Bragg condition. If you go slightly off the Bragg condition, this won't be as strong, and there won't be as a result, one of the waves, the outgoing wave, is not as strong as the incoming. You don't get this standing wave pattern, you get absorption. So if you did a numerical simulation of this, you'd see that as you play with the angle, just when you get to the Bragg condition, this interference pattern, standing wave pattern, appears. And this is called the Borman effect. And by the way, you could do the same thing. The same thing applies to a multi-layer, say tungsten and carbon, but in that case, things aren't so nice because you're not looking at atomic planes, you're looking at thin amorphous layers. So, so there is material, there are atoms, and there are with electrons in this region. So the diagram doesn't hold over that well, but the same effect is happening, it just isn't effective. So multi-layer coatings will never give as good a reflectivity. This is just more of the same. We used to think that polysilicon was going to go at 13.5 for the lithography. Oh, I'm sorry, it is 13.5. We used to think 13.4. I'm not sure what these numbers are for. But anyway, when I wanted them, I just looked them up earlier today on our website. So here are some examples then for silicon. We've seen these before, but they start to make more sense to us now. And then we're going to look at molybdenum. Molybdenum will be the high Z, 42 electrons. And it turns out that just, well, here, let me go back to silicon. At silicon, just around the L edge of silicon, which is around 99 eV, so just below 100 eV, silicon is doing a transformation to a 1 minus delta to a 1 plus something. It's actually crossing over. So in this region, the refractive index is 1 minus something. In this, below this line, it's 1 plus something. So this is a crossover, and the real part of the refractive index and the atomic scattering factor goes to 0 here. So that's why silicon, just below its L edge, is an interesting place to work, make coatings, because the real part, delta, is going to be about 0, and beta, it turns out, is also quite small. You're just below the absorption edge. So as you're increasing photon energy here, going up, 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 there's not much absorption until you get to the L edge, and you can kick out an n equals 2 electron, and now you got a lot of absorption. So just stay below that, and remember that these atomic scattering factors, the units are electrons. So this is, it's telling us that here, the absorptive part of silicon is acting like it's only about 0.1, 0.2, 0.3, 0.4. It's acting like it's less than a half electron effectiveness, okay? And the real part is acting like it's no electrons. It's just not in there, okay? So this must be raising some questions, but let me show you the Moly curve. So if you put Moly and silicon together, which a fellow named Troy Barbie did, he got a startling reflectivity, and later it was interpreted in terms of what's shown here. So for the molybdenum, the absorptive part, very surprisingly, even with 42 electrons, was acting like there was only 1 electron playing a role in absorption. And the delta part, the real part of the scattering factor, was acting like 15 electrons. So it's acting like 15 electrons are scattering with very little absorption. And the silicon, for its place, was acting almost like vacuum, not quite. So those two put together make for that Moly-silicon coating. So this is, the question was asked before, well, how do you make these coatings? So here's an example. These are called sputtering heads. So there's a target material, let's say the high Z and the low Z. So it could be tungsten and carbon, or molybdenum and silicon. And there's electric fields set up. There's an argon gas in the middle, and argon gas, it's ionized, there's a plasma, and some of the argon ions, the heavy part, the ions, are going down and they're crashing into this target material. It's a solid material. And those argon ions are knocking off a bit of molybdenum here and a bit of silicon here, and it's going on all the time. There's shadow masks, which are important, but not important to understand how it works. So there are going to be, because of the argon ions bombarding this, that's the sputtering process. Sputtering meaning knocking off atoms, okay, of the different materials, and they're going up, and up above it is this big plate, rather large plate, that's rotating around. So here's the rotation of the table, and there are little openings in different places, and where you're going to put 3 different, as shown here, 3 different mirror substrates. Maybe they're just flat circles, or they could be spheres, okay, or ellipses, but let's just say they're flat or spheres. And as this table rotates, this one picks up some of the high Z material, and then as the table rotates a little bit further, it picks up some particles from the low Z material, and then it goes around for another pair later. So it gets Moly-silicon going around, Moly-silicon, Moly-silicon. If you wanted to have B4C in there, you'd have to have a 3rd and a 4th sputtering head, as they're called, okay? The shadow masks are mainly to make it uniform coating across the substrate. So a bunch of rather practical engineering of how can you control the angular deposition onto these mirror substrates. And then for uniformity, each of the mirrors is rotating as it goes around. So, so this would go through a few rotations above each of the heads for uniformity. So did I help with that explanation?
Yep.
Okay.
Professor?
Yeah.
So with this rotating table setup, how do you control the thickness of the layer? Because
Oh, yeah, a good question. Yeah, because how slow it's going will determine whether it makes 3 rotations or 5 rotations here. And you have your voltages that are set also. So you have some control over the emission rate of atoms coming up, and they are atoms. But how long you spend over each head will give you what the thickness is. And what's very nice about this sputtering process, it's all electronically controlled with good feedback. So you can make one of these mirrors, a very high quality mirror with a very precise despacing, and you can come back months later, you know what the voltages and everything else are and the currents. And you might do a quick trial just to check that you're right, but you can really reproduce the coatings. Okay? Oh yeah. So this is a beamline at the ALS. For those who we've looked so many times at that web page where you look things up, and I've told you that Burton Henke was he started this all many years ago. But Eric Gullickson, who's shown here, he is the guy. If you have any questions on those atomic scattering factors or making a multi-layer mirror, you should go find Eric Gullickson. He's in building 2, I think on the 4th floor. And he's a very helpful guy. And anyway, he has this beamline where all of these things are measured that we've talked about, okay? And these are 2 former students. Andy Aquilar is at SLAC. If we could go on a tour of the FEL there, he would be our guy. And Franklin Dollar they were both engineering physics majors, by the way. And Andy got an AST, his PhD. Franklin went to Michigan to get his PhD, and now he's a professor at Irvine. And Yanwei Liu got his PhD in AST, and he's also at SLAC. Okay, so this is where these multi-layer coatings are made and measured, and just glancing incidence reflectivity, and they're forever upgrading the delta and beta values. And by the way, another project that's also possible is the optical constants here, the deltas and betas, you know, they don't have the fine details near the absorption edges. So for people who are doing XFs and NEXAFs, this is for designing mirrors and certain gross features of the optics. But if you really get into high resolution absorption or emission or anything like that, for instance, with NEXAF and XFs and that could be a project. Someone could tell us, okay, what is the limitation of these optical constants? This is an example of an early KB pair. So we've called them Kirkpatrick pairs. Notice that they're giving a high demagnification. They took bending magnet radiation at the ALS. This was the first beamline at the ALS. We had a running synchrotron and no beamlines, and this was the cheapest, fastest, quickest thing we could do. And so they used bending magnet radiation, KB optics. This was done by Jim Underwood and Al Thompson. And they set an aperture, and they image the aperture onto a target, and then choose by having different mirror pairs with different multi-layer coatings. They could look at 8, 10, and 12 keV. The angle of incidence was roughly a degree, And roughly the bandwidth for these multi-layers is something like 3% or 4%. Okay, and so this radiation is focused onto the sample, which then gives out fluorescent emission from whatever atoms are there. And this is raster scanned, and you make a map of what did you see, in this case, what did you see from iron, or what did you see from nickel, or anything else. Anything that's there, you can catch. And with a decent solid angle of collecting the fluorescent X-rays, this system can get, as you see, femtograms per square micron. So they can measure parts per billion. So if there are parts per billion in your sample, they can measure it, okay? This earliest, what we called microprobe, because it focused down to about a micron. Again, it was the first one. This is what I showed you at Spring 8. They now use very well-made elliptical coatings to get down to 7 nanometers. So the world has changed a lot since this was done. And this is from a sample from a company in Ohio that was making solar cells, and all of a sudden the solar cells weren't working, and they heard about this beamline and they brought it, and they found that there were all these spikes of iron contamination, and that was spiking their solar cells. So they said thank you, went home and got rid of the iron impurities. This is some images. This is a normal incidence. So this is not glancing incidence like the spiral galaxy was hard X-rays and glancing incidence. But now, what about making multi-layer coatings on 2 optics? This one, okay, well, the primary would have a coating along here, and the secondary mirror, and you can just ray trace, see how the ray trace goes. And here's an image of the sun projected onto a CCD detector, and this is an example of that. And so this is done at, it says 17.3 nanometers, and this is the energy in EV. So this was also using polysilicon coatings. And so this is showing the solar corona and the flares and everything else. And this is looking at emission that's dominated by emission from iron that's been ionized 8 times or 9 times. That's how many electrons were removed. And that is an ionization level that one expects in 100 EV plasma, a plasma with an electron temperature of about 100 EV. Okay. Oops. Oh, I'm sorry. I went the wrong way. So this, the telescope, I think it was called TRACE. I don't see it, but I think it's the TRACE telescope. And here are some of these spectacular images of these loops. Okay, and so there's plasma material that's going up and coming back down, and they're following magnetic lines. So these images are used to study plasma physics of the sun's corona. Okay, and here's one of the nicer ones. Okay. And I just wanted to point out to you that sometimes with multi-layers, you don't want them to be too narrow. You don't want them to, because if you're, for instance, in the high harmonic folks will be interested in using probing with very short pulses under 100 attoseconds or 200 attoseconds. And if you have too many coding pairs, that sets the bandwidth. So 40 layer pairs would give you something like 1/40th bandwidth at the photon energy you're working with. So it turns out that sometimes it's better to have a smaller number of layer pairs. Here it's shown 10 bilayers, so that you'll have a broader spectrum. The reflectivity won't be as high, but the width, the spectral width will be broader, and you can reflect an image and do spectroscopy with shorter pulses. And this was the same Yanwei Liu I told you was at SLAC, who was in one of those pictures. And I think that's all we have for today. Yeah. Oh, this wasn't in there before, but I showed you how to do interferometry. And years ago, I was learning how to make holograms, and this was a birthday candle. But when I got all done, I hand colored them and sent them around the Christmas cards, which I found many, many years later in different people's labs. And that also reminds me, just as we were ending last week, I was just about to say, okay, that's the end. And I got a phone call and I said, so I don't remember what you heard, but what I said was, oh, that's Stan Goldstein. I have to answer the phone. So who is Stan Goldstein? It was his 98th birthday the day before, and he was my undergraduate faculty advisor. So he plucked me out of high school and took me to his little university. And he and I have been close ever since. And so when he calls, I answer. Okay, do we have some questions? So I think next time we'll start on coherence, and Difan and I will make up a homework problem for you, but I'm going to try and make them relatively simple, just so that you get a sense of numbers, like what is the glancing incidence angle for 10 keV? It's pretty small, but also where we might want to do a curve of something, we'll just use the website. So the homework problem will be more about how to use the website, give you some problems on that. And I think many of you have identified projects you want to do, and I would suggest that if you have partners that you're going to collaborate with and coordinate your presentations and your material, that you get onto that soon. Okay, so meet with your partners. And if you don't have a project, send me an email with whatever ideas you have or what you're open to, or just let's get a dialogue going. And you can do your own project or you can work with someone. Any comments before we close? Okay, see you Thursday.
Thank you.
Bye-bye.